What's up, everybody? It's Dan from SageMathTutoring.com, and back with a video covering some SAT practice test questions. This time it's test questions for practice test 6, and I made this video for a student. These are the ones the student got wrong. All right, number 2. And by the way, this is the second module, and it's actually the more difficult module. So my student did quite well in the first module and was moved into this second, more difficult module. All right. In triangle RST, the measure of angle R is 63, which is the following could be the measure in degrees of S. Well, I would definitely draw that situation. So we have a triangle here, we have R, we have S, we have T, and apparently this right here is 63 degrees, which is why it could be the measure of S. Now, we don't know much about the measure of S, which we'll call that red X, but we do know for sure that this angle plus this angle plus this angle add up to 180 degrees. Let's go ahead and call this one Y right now, and hopefully we are all understanding that 63 plus X plus Y is going to be 180. So we have an X and we have a Y. And therefore, hopefully we all understand that X plus Y is going to equal 180 minus 63, which happens to be 117. So these right here have to be 117 when you add them together. So X plus Y equals 117. So we know for sure that whatever this red X is, it has to be less than 117. Okay, so that's why answer choice A is the answer. Okay, looking at this one, y is greater than 4x plus 8, for which of the following tables are all the values of x and their corresponding values of y solutions to the given inequality? Now, what this means is they're basically saying if you plug in x and you plug in this value for y, does it result in a true statement? Okay, now let's take a look at answer choice A. We can plug in 2 for x and 19 for y and kind of see what happens. Now, we're going to be ultimately performing 3 tests here. So let me just do this really quick. It is the case that they're suggesting that when x is 2, y is 19, we will be inspecting that. We will be inspecting when x is 4, y is 30. We're going to see if that's true. And we're going to be inspecting when x is 6, y is 41. So in the top one, it would be 19 is greater than 8 plus 8. I think we all agree that is true. This one would be 30 is greater than 16 plus 8. 16 plus 8 is 24, so that's true. And this one is saying that 41 is greater than 24 plus 8. 24 plus 8 is 32, so that's also true. So the answer to this one is A. All you had to do is just test the x and y coordinates to see which one was true. Another way of going about this is you could have plugged the original inequality here into Desmos, okay? And I'll just kind of draw it for now instead of doing that. So it would have been a line that kind of goes up like this through 8, and it would have been the case that the region above would have been shaded. And one of the things you could have done is you could have just looked at these points and seen if the points had fallen in the shaded region. If these points had fallen in the shaded region, then you would know for sure that those points do indeed work, okay? So to be clear for my student watching, you absolutely in Desmos can write this, even with the inequality symbol that is very much there on like the keypad, okay? So that's that one. Okay, the function f is defined by f of x equals that. For what value of x does f of x equal 5? So for my student watching, it's really important to know that I know this is kind of like weird function notation. One of the things I actually said in session relatively recently, I think, is that, all points really have an x coordinate and a y coordinate. That's kind of what we're used to. And whenever you see a statement written like this, where it's like f of x equals something, this x corresponds with that, and this corresponds with that. Okay, so that could be helpful to remember because you could sort of think of this question as saying, when y is 5, what does x equal? Okay, I'll say that again. When y is 5, what does x equal? So when y is 5, now you could treat this as though it's y, by the way. That's another thing you should know. Okay, you could treat this f of x like it's y. So when y is 5, what does x equal? Now, this is something you could plug into Desmos if you want, which is actually not a bad idea. Um, you could literally plug in this equation and it would give you the answer by giving a vertical line that cuts through the answer. So I'm actually going to do that right now. Okay, so when I plugged in this equation, it gave me this vertical line here that cuts through clearly the x value of 3, so that means that 3 is the answer to this problem. So this is a great one for Desmos, I would say. The primary insight is to recognize that this is secretly asking when y is 5, what does x equal? You also need to know that whenever you see an f of x, you could kind of replace it with a y, and then kind of take it from there, plug it into Desmos, and you're good to go. Now, some people might want to know, how do you solve that algebraically without Desmos? Well, this would just be a matter of recognizing that these denominators are annoying, and therefore you can multiply both sides of the equation by the denominator. You can multiply both sides of the equation by 7, which means it really amounts to multiplying all the numbers by a 7. That would cancel these, and then you would have 35 equals 9x, because the 9 is still left over, plus 8. And then you would just solve that in the typical way. Okay, the graph models the number of active projects a company was working on X months after the end of November 2012, where X goes from 0 to 6. Okay, cool. According to the model, what is the predicted number of active projects the company was working on at the end of November 2012? So, one of the things I told my student recently is when you're dealing with a linear model that sort of describes a real world situation, I maybe this is time and maybe this is height or something, okay? I had mentioned that the y-intercept is always the amount you started with at the beginning of the observation. Okay, and that would be the y-intercept, whatever that value is right there. Okay, now that also applies to nonlinear situations. For example, if we had a quadratic situation written in standard form like this, where you have this constant here, okay, well, that in that case would also be the amount you started with, if it's the case that this describes some kind of real world situation. Maybe this is days gone by, maybe this is the amount it costs to, um, maybe that's the amount it costs to rent a boat or something. I don't know. So that's important to know that it applies to a quadratic situation as well. So to recap, if you have a real world scenario that's being modeled by either a quadratic or a linear, this y-intercept is the special number that lets you know the amount you started with. So that's really the insight that's necessary for this, because they told you what this graph means. Now it's very boring, so you have to sort of, you know, begrudgingly read it and understand it, right? So the graph models the number of active projects. Oh God, I'm falling asleep already. A company was working on X months after the end of November 2012. So what does that mean? That means that this is November 2012, and these are all the months after November 2012, right? So this moment in time is November 2012, right? Because the x-axis typically has to do with time. I think that's another thing to remember. So what is the predicted number of active projects the company was working on at the end of November 2012? In other words, here, that's the y-intercept. So that's going to be 5. Okay? So if you have to pause that, read it, and think about it, that's clearly the answer. Okay, what system of linear equations is represented by the lines drawn? Well, I mean, you could throw all of these into Desmos and you could find, you know, which ones would look like that. Okay. I'm thinking, though, that it's probably, that would be a little tedious in my opinion. And I think a faster way is to realize that clearly the point 8 comma 0 exists on both of these graphs. So therefore, on both of the equations, when x is 8, y is 0. So let's set y equal to 0 and see if x ends up being 8. If we set y equal to 0 here, that would be 8x equals 32. X would therefore be 4. So that's gone. Okay, so in case you didn't follow that, I'll say it again. When y is 0, this would end up being 8x equals 32, and then x would be 4. Now we want x being 8 when y is 0, not 4. So that's gone. When y is 0 here, that would be 8x equals 32. X would therefore be 4. So that's gone. When y is 0 here, it would be 4x equals 32. X would therefore be 8. So that one works. Check for that one. Let's do this. When y is 0, it would be negative 8x equals negative 64. And negative, or x would therefore be 8. So that would work. Now, I do want to be a little careful, though. Let's look at this one, too. So when y is 0, it would be 4x equals 32. X would be 8. So that checks out. When y is 0 here, it would be negative 8x equals negative 64. So that actually checks out as well. So it's a good thing we looked at both of these, right? Because for all we know, one of these is going up like that, and it does indeed cross there, but it's not the same as this scenario. Okay, so it is important to sort of recognize that you could have more than one answer choice that reflects the fact that there's this point of intersection at 8 comma 0. So then the question is, well, what do you do now? Well, what I would do is I would just inspect this one on Desmos, and if that one works, if that one does indeed look exactly like this, well, then that's the answer. And if it's, of course, the case that this doesn't work, well, then D is the answer. So we only really need to inspect one of them. And upon inspecting answer choice C, we have this, and that's clearly different, right? That's clearly different than the graph that they drew. So we know it's answer choice D. Okay, so this was answer choice C. Hopefully I said that correctly. This is answer choice C, if you look at it. And it didn't work, so therefore answer choice D. Note, of course, how answer choice C did have that point of intersection, though, which is why we had the check marks. Okay, the solution to the given system of equations is xy. What's the value of 6 times x minus 2? Yeah, very strange. For my student watching, probably there's a temptation to maybe distribute here because typically that's like what you would do. Maybe there's a temptation to distribute here to sort of make it look normal, a little bit more normal looking. However, this is what I would say is a classic example of how the SAT math gives you sort of like a very specific batch of unique type of problems that other standardized tests don't give, and you weren't faced with even in high school. You haven't been faced with in high school. So um, I would say Desmos maybe not the best idea because even if you plotted these, it might not be clear what exactly to do with this information. What I would do is I would note that they're not asking for X. We're so used to them being like, what does X equal or what does Y equal? Notice how they're not asking that. They're asking for something like for what some kind of expression is. Now, I've learned through experience with SAT prep tutoring that whenever they ask for like a strange expression that could be a code, that they want you to actually get that by itself and then have some number over here, which is the answer. So they want you to rearrange this whole situation so that you end up with a 6 times quantity x minus 2 on the left by itself, and then you have your answer on the other side. Okay? So then the question is, well, how do you do that? Well, I feel like we all can maybe see that there is an opportunity to immediately cancel these out if we were to add the entire bottom equation to the top equation, which, by the way, you are allowed to do. Okay, you are allowed to do that. Well, it would be this plus that, which would ultimately be a 2 times x minus 2. And it would be negative 4 blah plus 4 blah. These would cancel, wouldn't they? Cancel, cancel. So that's just a 0. I don't feel like I need to write that. And then we would have equals these added together, and that would be a 955. Now, your instinct might be saying, oh, okay, divide by 2, solve for x from here. But no, no, no. Remember, we're not trying to solve for x. We're trying to figure out what's going on with 6 times quantity x minus 2. Well, it's almost like we're there, but we just have to multiply that by 3, don't we? We just have to multiply this by 3. So let's multiply literally both sides by 3. Wouldn't that give us a 6 times x minus 2? And then 559 times 3 is 1677. And even though it might feel awkward calling something like this the answer, that is the answer. Okay? We found what they were asking for. The positive number A is 2,241%. Okay? Interesting percent of the sum of the positive numbers B and C. And B is 83% of C. What percent of B is A? Yeah. So I would just write sort of a slew of equations that represents the situation they described. So looking at this statement here, let's directly translate that. A is just A. The word is equals. Percent always needs to be as a decimal if we're translating into an algebraic equation. How do you turn percents into a decimal? You do it by moving the decimal rather, twice to the left. So that becomes 22.41. The word of means multiply. And then there's this sort of interesting quantity. The sum of the positive numbers b plus c. So that is a quantity where it's this entire quantity of b plus c. And of course, we're noting that b and c happen to be positive. So let me just, in the name of spacing this out a little bit, bring this down here as one of our equations that could come in handy. B is 83% of C. Great. So that easily translatable. B is just B, is equals. This is as a decimal, moving that decimal to the left twice. Of means multiply, and C is just C. So that is another potentially helpful equation. Okay, so we have two equations here. What percent of B is A? Okay. So ultimately, we're dealing with a system of equations, okay? And they're asking what percent of B is A? Well, I'll just say from experience that since they're only mentioning two variables here, okay? Since they're mentioning only two variables, we want to create a scenario where we're only dealing with those two variables, but the problem is we have this pesky C that's hanging out in our face. So we need to find a way to get rid of C or replace it with something so that we have an equation that only features A and B, okay? Because if we had an equation that only featured A and B, then we could kind of rearrange it and figure out the answer. So let's say that when it comes to this second equation, if we want to sort of get rid of C, you can do something somewhat counterintuitive, which is to, in a sense, solve for it briefly in one of the equations by, in this case, dividing both sides by that 0.83. And then we have this sort of ugly number here, but it's not the end of the world. So we know now that anytime you see a C somewhere, you could always replace it with this, okay? Well, that's what we're going to do. We are going to update this, okay? We're going to update that to say A equals 22.41 times B plus this thing, okay? So instead of saying C, we're going to say that. And then we could solve this one, okay? Well, at least, I don't know about solve it, but let's simplify it at least, okay? Now, once again, our goal is to still say what percent of B is A, okay? So, yeah, let's actually analyze that really quick. It's asking what percent of B is A? Maybe we should just pause and get clear on what our ultimate goal is. It's saying what percent of B is A? In other words, what percent, which is some p-value, we'll call it, of is multiplication, B is just B, is equals an A. So that's kind of like saying get A by itself and then have B on the other side and find out what B is getting multiplied by. And that number over here is the answer. Well, we already kind of have A by itself. Well, we do have A by itself, okay? And I feel like if we just kind of messed with this side a little bit, maybe we could figure out the answer from there, okay? Now, this is probably a good Desmos situation because you would have to distribute that there and there. So you would have a scenario where it's like 22.41b plus 22.41b over 0.83. But let's be very clear that this scenario could also be rewritten as 22.41b with the sort of clunky decimally fraction off to the side, with this sort of b hanging out to the right. Okay, so for my student watching, just know that this scenario, we have something with the variable on top of the numerator over some other number. You could kind of tease out this fraction and put it to the left. Now, the reality is that this here is a scenario where you have two like terms. You have something times b plus something times b. So what do you do when you have like terms? Well, you keep the variable and you add the coefficients. So it's going to be 22.41 plus 22.41 over 0.83. So we are most definitely getting closer to the answer. Remember, our goal is to have A by itself and then mess with this until we have a number that is getting multiplied to B. Well, we're so close. So this is the part where I would use Desmos. I would literally be like, okay, 22.41 plus this equals what? So Desmos gave me 49.41. So this is A equals 49.41 times B. Now you could say, oh, okay, I found the answer. It's this. But remember, that's the percent as a decimal. So in order to turn it back into a percent, you must move the decimal 2 times to the right. So the percent would be 4941%. 4,941%, and that's right here. A circle has center G, and points M and N lie on the circle. Line segment, okay. Yeah, here's the circle. There's G. M and N are on the circle. Line segments MH and NH are tangent to the circle. The radius of this circle is that, and the perimeter of quadrilateral is that. What's the distance between G and H? Okay, there's no way I'm not drawing the heck out of this. So I'm just going to take a shot in the dark and say that that's M, and I'm going to say that that's N. I don't really care right now if it's placed in the exact place it should be. Now, line segments MH and NH are tangent. So that means that there is in this case, in the case of my diagram, there'd have to be an H floating like this. And when they say tangent, I mean it's sort of grazing, okay, like that, sort of, connected like this. That's the scenario they're describing here, okay, for my student watching. That's important that you understand that. Tangent means it's like a segment that's kind of resting on the edge of the circle. Now, I want to pause there because for my student watching, I'm hoping my student understands and everyone else understands that when you have this scenario, these will equal each other. If you have a point on the circle and another point on the circle, and you have a common outside point that they both have tangent lines going to, well, then these tangent segments, we could say, are congruent. They're of the same length. So that's a nice mental note to make. If the radius of the circle is 168, all right, so as soon as they say that, I'm thinking to myself, well, let's imagine this radius, and we'll call that 168. Let's imagine this radius, and we'll call that 168. Now, you might be wondering, why am I just choosing to connect these? Why am I just choosing to connect these? Well, the reason I'm choosing to connect those is because, first of all, they're mentioning a quadrilateral called GMHN. Well, I just formed it, didn't I? I just formed GMHN, right? And a quadrilateral is a four-sided figure. So that's one reason I chose to draw those radii, such that they connect from the center to these points, because I foresaw that I'd be drawing a quadrilateral. But another reason I did that is because there's an interesting phenomenon to know about the radius and the tangent line. Remember, for my student watching, this was what we call a tangent line. This is a radius. It's always, always, always the case that the radius connected to a point and a tangent line coming off that point form 90 degrees. So that's 90 degrees. Okay, so I'll say that again. A radius connected to a point on the circle and a tangent line off the point on that circle always form 90 degrees. So a radius connected to a point on a circle and a tangent line off the point on that circle always form 90 degrees. Clearly not drawn to scale, but let's go with it. Okay. The perimeter of the whole quadrilateral is 3856. We'll worry about that later. What is the distance in millimeters between G and H? Right. So it is the case that we could call this X and this X, because remember, I already said that this tangent line length has to be the same as this tangent line length. So we sort of have this quadrilateral, and I'll just draw it like this for now, okay? And we have this quadrilateral. Here's the blue parts. We'll call that X, we'll call that X. Here's the yellow parts. We'll call that 168, we'll call that 168. We also know that's 90, that's 90. We have this quadrilateral such that the perimeter equals 3856. So what that means is it's going to be X plus 168 plus 168, and that's going to equal 3856. So we have 2x plus 168 plus 168 is 336 equals 3856. 3856 minus 336 is 3520. Divided by 2 is 1760. So we know that that's 1760, and that's also 1760. And they want to know what is the distance in millimeters between G and H. So ultimately, they want to know this distance, because this is G, this is M, this is H, and that's N. All right. Now, you might be wondering, well, why am I bothering solving for X? Honestly, I don't know. I don't know. I just feel like if we found X, then that would move us in the right direction and probably enable us to find the answer. Okay, so that's kind of where I'm coming from. And I'm already seeing by looking at this that I'm right. All right, so, and the reason I'm right is because now we can inspect a little bit more closely. Let's get rid of these X's because we know that these sides are 1760. Ultimately, we're trying to find this. Now, let's be very clear. We have this sort of red triangle here. Let's only focus on this red triangle. Of course, there's another triangle above it, but let's only focus on this red triangle. Isn't it the case that this red triangle is a right triangle? Because that's 90 degrees, right? How did we know that that's 90 degrees? Because the whole tangent line, radius thing. Remember I said radius always forms 90 degrees with the tangent line. Okay, that's 90 degrees. Therefore, this triangle is a right triangle. Therefore, the Pythagorean theorem applies, correct? Pythagorean theorem applies to this. And that's 168, that's 1760, and let's call this C, because typically when you're doing the Pythagorean theorem, it's a squared plus b squared equals c squared. C is the hypotenuse, right? C is the hypotenuse of a right triangle. Well, we'll call this C. We are on a mission to solve for C right now. So That's 168 squared plus 1760 squared. That will be c squared. And 168 squared is, that would be 28224 plus 1760 squared is 3097600, and that's c squared. And adding those together would give you 3125824, and that equals c squared. I think my student watching understands that now in order to get the answer, we have to take the square root of 3125824, and believe it or not, that turns into a nice number called 1768. Okay, so that is this distance, because this distance is the hypotenuse of the red triangle, and we just found it. Let's note that is what they were asking for. They wanted what's the distance between G and H. We just found it. 1768. I do not know of a better way of going through that. That's clearly a hard one, and it makes sense that it's hard because this is problem number 21 in module 2, and it's the harder module because my student did well on the first module. So that means that they gave my student the more difficult module. Okay, so that's how you do that. Hopefully that was helpful. I will talk to you later. Bye.